Okay, guys, anyways, last week we finished until this chapter here, this question here, right? This was done already, right? This one here, the calculation one. This week we're going to finish off the last two questions in the booklet. Then after that, we're going to move on to a new chapter already, guys. So once again, you have a certain amount of time. In this case here, you have exactly 7 minutes. Please attempt this question here. Huh? Why is it the same? It's because this shows that in your IGCSEs, they love to ask you to define specific heat capacity. So you better know how to do it. 7 minutes, guys. Please attempt this right now, and then we will discuss the answers immediately.
Oh, do you know Justin? No.
Oh, sorry. Okay, Shinin, I think you should be done with this question here, right? Yes. Evan should be here also, right? Ah, Evan is here. Hey, Evan, you're done with this one here? Okay, anyways, I want to highlight this again, guys. For those who have forgotten how to define this, you can define it by simply recalling the formula Q equals to MC theta, guys. If you can recall Q equals to MC theta, then C would have been Q over M theta, right? Which in this case here, specific heat capacity is the amount of energy needed to change 1 kg of a substance by 1 degree Celsius, guys. Okay, so this is exactly how I would say it out. Amount of energy needed to change 1 kg of a substance by 1 degree Celsius. Okay, amount of energy needed to change 1 kg of substance by 1 degree Celsius. Very standard question, very standard answer. You must know how to do this. Yeah, I can refer to the notes I have the statement there already. Anyways, from here, the next part here, they ask you to calculate the specific heat capacity. Once again, if you want to calculate the specific capacity, it's basically using this formula. In order to calculate the specific capacity, you'll need the heat energy, you'll need the mass of the object, and also the change in temperature, which if you identify here, did you use your mass as 800? No, you're supposed to convert it into 0.8 kg. Because mass standard unit is in kg, then this is obviously your heat energy, and this is obviously your theta. So from here, it's literally 8,700 divided by 0.8 divided by 12 here, right? And if you press in your calculator, you should get 950. 906, good. 906.25. What's the units here?
Joules.
Degree Celsius, right? But when you have this answer here, can you write 906.25 here? No. How many maximum significant figures can you write? 3 only, and don't forget your units, then you'll get banned your full 2 marks. Okay. Then finally, this last question here, they say state and explain a method of improving the accuracy of this experiment. Now, guys, I want to highlight this. This one here, right, also always comes up in your exam. You have to understand that all these heat energy questions they have one assumption, right? I think I mentioned this last week. What is the assumption that we make when we calculate the heat energy questions here? What's the assumption? We assume that all the electrical energy is converted into heat energy, and all this heat energy is fully transferred to the aluminum cylinder here. In a real life scenario, will this be possible? No. Where will the energy go? Good, it will be lost to the surrounding. So one way to improve the accuracy is by reducing the energy loss to the surrounding, right? So the most common method is to insulate the block, right? If you insulate the block with some insulating material, or even put a cap on the insulating block, onto the aluminum block, right? This prevents the heat energy to be lost to the surrounding, right? Which will ultimately improve the accuracy of the experiment. So you're supposed to say something like insulate the aluminum cylinder. This prevents heat energy. So do the last question. Then we'll move on to a new chapter already. Eight minutes, guys. You have 8 minutes to attempt the next question. Okay, everyone, I think you should have enough time to attempt this question already. Let's go through the answers real quick here, guys. From here, you see that figure 5.1 shows a plastic cup. The cup contains sand and electric heater and a thermometer. Power of heater is this amount, so they give you the power first. The mass of the sand is this amount. Yet again, it is not in the proper units, so you change it into the proper units first before you do any calculation. The initial temperature is 20. This is not the change. This is just the initial. And this is the time taken, right? Which is, once again, not the proper units, because time should always be measured in seconds. The temperature is recorded until the temperature stops increasing. The highest temperature recorded was 33. So straight off the bat, I know that the change in temperature should be 13 degrees Celsius, right? Right. Then from here, first things first is they ask me about energy. If I were to do this question straight up, I would think that Q is supposed to be MC theta. But if I do this equation here, I realize that even though I have the mass, I have the change in temperature, I do not have the specific capacity. So which means to say I actually cannot use this formula. Instead, I should ask myself, what information do I have that can help me find energy, which is the basic formula, right? Good, very good. Power is equals to energy over time. Right, and straight away from here, you're supposed to say that energy is equals to power multiplied by time, which is supposed to be 50 multiplied by 120, which will give you 6,000 joules. Right, make sure you write 6,000 joules. Okay. Then, after that, they ask you to calculate the value of specific capacity. Once again, Q is equals to MC theta, and C must be Q over M theta, right? Which in this case here will be 6,000 divided by the mass of 0.55 divided by the change in temperature of 13 degrees Celsius. Right, and if you press this in your calculator here, you'll get 839 joules per kg degree Celsius once again. 839, is that right? No, it's 839 joules per kg degree Celsius. And then finally, the last question here, they say explain why the specific capacity of sand may be different from the value calculated in A. Once again, why it will be different is because we are assuming that all the energy from this heater is converted to the water and the water is converted back into the thermometer. But in reality, we know for a fact that energy is always lost to the surrounding, and it is lost to the surrounding to be exact, right? And because it is lost to the surrounding, you'll see that it's always going to be the same thing over and over again. Some electrical energy is lost to the surrounding, so the specific capacity calculated is lower or it's different. You don't even have to say it's lower. You can say it's different, it's acceptable already if you're not too sure. So you're going to say energy it's lost to the surrounding. Specific capacity will be different. Okay. Anyone's got any questions for this part here? Took a video. Oh, 几时？几点？ It's open to the public. Okay. Time. Why you look like your sister? You look like your sister. Okay. Anyways, if you got no questions here, guys, yeah, I might go actually for something Wesley Hunter. Now I've got a good excuse. Where is it? What the hell? Okay, anyways, last question. Last thing we're going to do today, guys. Basically, we're going to move on to the new chapter already. But as I move on to the final chapter of thermal physics, this means to say what we're going to do is today we'll most likely finish up the syllabus for thermal physics, right? Then after that, we'll do one revision for the whole thermal physics chapter. Then it's going to be test once again, guys. Yeah, but next week don't come to the center. I repeat again. What the hell? You thought it was this week? This week? No. Next week, everything will be converted online as. Oh yes, I will end of the week at 1, 2. Oh, 1, 2, 3. When is your end of the year exam going to be, Xinyan? 1, 2, 3, you mean to say general physics, thermal physics, and wave physics, right? When is it? June 13. Okay, I'm not holding enough time. Just enough time. Okay. Anyways, moving on to the final chapter here, guys, we are basically going to understand the main differences between conduction, convection, and also radiation. If I were to categorize all of them together, in a very simple manner is that all three of this is a form of thermal transference. Okay, heat can be can be transferred through conduction, heat can be transferred through convection, and heat can also be transferred through radiation. In order to have a very brief understanding of how conduction, convection, and radiation is, you have to imagine today 3 of you guys went to camping together. Okay, so as soon as you reach the campsite, obviously what you're going to first do is you're going to start the campfire, right? For sure, if not, how can it be a camp if there's no campfire, right? So anyways, as soon as you start your campfire here, yeah. Right, but anyways, as you reach the campsite here, right, 3 of you guys are, one of your friend is an idiot. Okay, let's draw him in this color here. Okay, yes, it's a him. Okay, this idiot here is a little bit hungry, so what he does is, right, he takes a metal stick and he roasts marshmallow on it. Okay, it's a metal stick, right? Oh, Evan, you know it. Okay, but anyways, the second guy, it could be you lah. And for diversity's sake, let's include a female in this story. Okay, this female here, usually they say that women are a little bit cold-blooded, right? Oh, shit, sexist remark, right?
Where is that?
Wait, I'm not done drawing. She's very cold, right? So what happens is she puts her freakishly long hands above the fire. The fire, they put right above the fire. Okay. And then finally, there is the last guy, which is probably you, right? The last guy is very lazy. Okay. And because he's very lazy, as soon as he reaches the campsite, he sleeps right next to the fire. Right. He sleeps next to the fire in a sleeping bag that conveniently looks like the ship drawing also. But bear in mind, it's a sleeping bag. Okay, he's a Kakuna. Yes, but he's sleeping right next to the fire. Okay. Now, all 3 of these guys are going to receive heat from 3 different scenarios. Let's start off with the green color guy first. How do you think this guy receives heat, Evan? Conduction, convection, or radiation? Which one? Good. The first one here is going to get heat through conduction. Now, conduction states that usually heat is transferred through a third-party object, guys. A third-party object in this scenario here is obviously going to be the metal stick used to roast the marshmallow. Because what happens is the heat from the hot end is actually going to constantly transfer to the other end here, and eventually it will burn his hand, right? Because heat is transferring there. Okay. Conduction is very special. Conduction states that it can only happen in 2 specific mediums. It could either happen in a solid or it could happen in liquid. It means to say conduction will only occur in solids or liquid. Okay, and obviously conduction states that heat travels from the hot end all the way to the cold end, right? Which is the same here, right? Which is what's happening here, right? Because the heat is going from the hot end, which is this side here, and transferring all the way to the cold end, which is where his hand is now. Right, so this is how conduction occurs. Okay, anyone has any questions for this part here? Okay, everyone, so far so good. Let's go on to the girl, the diversity girl. Why do you think that when she feels cold, she put her hand above the fire? Why not beside it? Why not around it? Or why not below? Very good. Everyone that has ever played with fire before, they always notice that fire is hottest on the top, on the higher side. Right. Fire is always hottest, right, on top. Why? Because this is a characteristics of convection. Okay. Convection states that, right, unlike conduction, heat will always travel upwards. I repeat again, convection states that heat will always travel upwards. That is the reason why, right, when you place your hands above the fire, you feel the hottest, right? Simply because the heat is constantly being convected upwards here. You understand? Right. And then convection is very special also. Convection can only occur in two specific things. They will either occur in liquid or they will occur in gas. Okay. If you've ever been onto a highway and you look very far into the highway, right, you'll notice that sometimes the highway they have like steam lines coming up, right? Have you ever noticed that before? You can't go there. Next time, right? What you do is, right, on the highway, especially on a very, very hot day, try to like gaze onto the furthest point of the highway. You'll notice that there are some steam coming on. Why? Because actually, right, what happens is, right, the sun is here, right? It heats up the tar road here. And then this tar road will actually heat up the air molecules here. And when it heats up the air molecules, you can slowly see that it kind of like steams upwards. And in fact, any hot surface can do the same thing also. It doesn't have to be the tar road. If you try to cook a pan without anything, right, and you place it under the sunlight, you'll notice that the air molecules are kind of going upwards, because once again, heat always travels upwards. Okay, this is the characteristics of convection. And finally, this last guy here, even though he sleeps beside the fire, he can still get a form of heat. What form of heat can he get? Radiation. Radiation is the most special among them all because radiation states that heat can travel in all directions. It doesn't matter if it's besides the left, the right, the top, the bottom, right? All heat, radiation can travel in all directions. Yeah, in a way they will get heat also. That's why even if you stand very close to the fire, you're not above it like the CG or not. Right? If you're beside the fire also, you'll feel hot because radiation happens in all directions. Okay. Okay. Then radiation also very, very special in the sense that it does not require a medium. It does not require a medium to transfer. In other words, it is the only one that can travel through space, which if you think about it, is essentially how the sun transfers heat to Earth, right? From the sun, in between the sun and the Earth is a lot of empty space, for sure, no air molecules inside, right? A vacuum all the way, right? But heat can still travel all the way from the sun, regardless of whatever position the Earth is, because we are receiving heat through radiation. Okay? Anyone's got any questions for this part here? Good, excellent, 100% absorption rate. So if you look at this diagram here, it's essentially a more simplified version of what I've been talking about. This guy is an idiot, so the heat will eventually travel to his hand through the metal stick. Right, this is conduction. The third party object is obviously the metal handlebar here. Convection states that heat will always travel upwards. Right, that's why the hot pan will always transfer the heat upwards here. And radiation states that heat can travel in all directions. As long as you're close enough to the fire, it will radiate heat towards you.
It comes in
Conduction. Conduction. Yeah, the so sour is because the steam is being convected upwards. But if you say the chopstick is getting hot, it's because it's touching the hot form. It could happen twice also. In fact, it could happen all three of it. At some point, right? Let's say, for example, at this point here, right? Is you can argue and say that it's receiving all forms of heat. Conduction is being conducted through here. Convection is being convected upwards here, and then radiation could come back also all this way here. I mean, in a way, You get what I mean? So if all three things could happen at the same time, but it depends on the situation. But they will never ask you this in the exam. So no need to worry. Okay. Good. Anyone else have any questions? Good, 100% absorption rate. So if you look at the statements here, these are essentially the key characteristics of conduction, right? Conduction transfers heat in a solid, usually involving a third-party object. Different materials will definitely have different conductivity. Good conductors are usually objects such as metal, as heat is easily conducted. Good conductors are generally things that can conduct heat and electricity. And the reason why they are easily conducted is because they have free moving electrons, guys. Same like what you see in your chemistry, guys. Right. It is due to the fact that it has free moving electrons. That's why metals can conduct heat and can conduct electricity. Okay. Then obviously bad conductors are things known as insulators. Insulators, they cannot easily conduct heat in them. And good examples of insulators are basically everything but metal. Wood, plastic, sand, glass, wool, rubber, right? All those things are basically insulators. Conductors are usually everything else. All the metals are good conductors. Okay? Anything you want to copy down here? Okay, done. If you're done, let's look at a simple experiment to test out different conductivities of different metals. Like I said, all metals are generally good conductors of heat, but not all metals conduct heat equally. If you look at this experiment here, it starts off with 4 different metals. I have iron, copper, brass, and aluminium, all these 4 different metals. At the end of all these metal bars, I'll stick a piece of Vaseline on it. Vaseline is a form of wax that will easily melt away when heated. At the end of the other side of the Vaseline, I'll stick a drawing pin here. So all 4 of these are heated at the same time. And the whole experiment is basically see which one transfers heat the fastest and melts the Vaseline, causing the pin to drop. Whichever one has the pin drop the fastest, that is essentially the best conductor of heat, right? So if you look at the so-called data here, right, you see that copper has the pin drop the fastest. This indicates that it is the best or worst conductor. The best conductor, and the worst conductor is essentially going to be steel. Even though all of them are metals, they will all have different conductivity, right? So yeah, this is just a very simple experiment to test out different conductivities of different things. Okay. Then after that, this part is important, guys. Pay attention to this. This here is basically explaining how heat is conducted through a conduction, guys. Okay, so let's imagine today this is a metal bar here. Inside these metal bars, there's obviously solid particles, right? The solid particles here. Let's imagine today, I heat up this end of the metal bar. Okay, I heat up this end of the metal bar. What happens is, right, as soon as I start heating it up, this specific particle starts to gain energy. And when they gain energy, they will vibrate in fixed position, vibrate until it can pass on energy to the adjacent molecule, the molecule beside it. So this guy will get energy already, right? They also start vibrating, vibrate, pass energy, 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 and vibrate. Okay, so this here shows that heat will always transfer from the hot region all the way until the cold region through the vibration of these particles here, passing on energy from one to another. Okay, so in your exam, they will ask you, or usually they ask you like, explain in terms of molecule how conduction occurs. You're supposed to mention this, vibrate, pass energy, vibrate, pass energy, vibrate, and so on. Okay, of course, a more structured manner will be as shown here. As the bar is heated, the particles gain energy and vibrate more. Lattice vibration occurs and free movement of the delocalized electron pass energy. This here is basically the free moving electrons in a more fancy term, right? Then thermal energy is transferred from the hot end to the cold end, right? And pass on their increased kinetic energy to the particles along the bar. Okay, liquids definitely have weaker intermolecular forces and have more space between the particles, which makes the vibration harder to transmit. So basically, in this statement here, they're saying that liquids are harder to conduct because the molecules are very far apart, which makes sense with the previous chapter we learned, right? We learned that liquids generally have a high specific heat capacity, very hard to heat up and very hard to cool down, right? Simply because the molecules are very far apart. Even if I vibrate, I have to vibrate them a lot before I start vibrating to other molecules, right? And obviously, gas have even more space and therefore have infrequent collision. This makes liquid and gas poor conductors of heat. They are poor conductors of heat. Okay. Anyone's got any questions for this part? Good, excellent. If you have no question, this part here is relatively important as well. This is basically understanding why convection states that heat travels upwards. If you ever cook Maggi mee before, guys, have you ever cooked Maggi mee before? Unless you're too privileged, right? If you ever cooked Maggi mee before, let's say when the water starts boiling, you'll notice that the bubbles always starts to go towards the edge of the sides of the pan. Have you ever noticed this before? Why do you think the bubbles go towards the side of the pan? Why? No, if the pan is hot, why would it attract the bubbles? In reality, yes, in reality, something must be moving at the bottom here, right? In a circular motion to pass the air bubbles towards the side, right? So let's imagine today I split this pan, this Maggi mee pan into half. And we focus on two specific particles only. One particle that is far away from the heat source, so they are relatively colder. And one particle that is relatively closer to the heat source, so they are relatively hotter. Right? If you remember from last week's chapter, we state that heat expands and cold contracts, right? You remember this? Right. So what happens is, right, today when these particles are closer to the heat source, obviously they gain more energy. And when they gain more energy, they will expand. Okay, so they will maybe expand slightly a little bit. I won't be like so夸张, but I'm just drawing to let you understand. When it expands, in terms of the density formula, what's the density formula again? Good, density is equals to mass over volume. My first question is, when I heat up this particle, will the mass change? Why will the mass change? It grows bigger, but why will the mass change? It won't, unless you disintegrate it totally, right? For example, paper, you burn it, then obviously you disintegrate the particles, then it will change mass. But water, I don't think you can disintegrate water particles, and thus the mass should not change. And I know for a fact that when I heat it up, it expands, right? So the volume increases. What happens to the volume? Sorry, what happens to the density when the volume increases? Density decreases. Very good. Is it increase or decrease, Macy? Oh, okay. Yes, because they are inversely proportional, right? And because of that, I know that when the density decreases, this will definitely cause it to float, right? Because the density decreases. Then it will start to float upwards. But when it floats upwards, it won't leave like an empty space here, right? It wouldn't, right? So what happens is, the colder particles will be displaced downwards. And when the colder particles are displaced downwards, what happens is Yeah, you have a continuously stream of cycles that keeps going on and on and on. This is what we call convection current. Convection current basically is the changing of the hot and cold particles over and over and over and over and over and over again. Right. So if you look at this statement here, but anyone's got any question for this one here? Okay, everyone okay? Well, my description is 100% absorption rate. Seriously, I'm damn good, is it? It's too easy. Yeah. But anyways, convection is a transference of heat in liquid and gas, for sure. Right. When liquid is heated, its volume will expand and thus the density will decrease. Okay. So the water above the heat source becomes warmer, expands and rises as it becomes less dense. The cooler, more dense water sinks to the bottom of the beaker and then once again is heated. This circulation of warm and cold water sets up a circulating stream known as convection. Of course, because this convection current is constantly moving like this one. So from the surface, you won't be able to see the convection current, but you have to follow this movement, right? You have to follow this constant movement of going up and down, up and down, up and down, right? Which is in this direction. Do you understand what I'm saying? Wait. It's not sticking to the pan, actually. There's a current that is moving the water. So the bubbles that are attached to the water moves towards the side. Right, because of the constant circulating stream here. Yeah. Okay. Yeah, but circulation current, convection current is not only in the Maggie water that you see. In terms of tectonic movement, you all know what tectonic movement is, right? You don't know what tectonic movement is? Tectonic movement is basically the movement of the Earth's the plates are. The plates on the surface is constantly moving, you know, right? Like for example, let's say 1,000,000 years ago, Malaysia is not where Malaysia is right now because the plates are slowly drifting and drifting. The continental plates were like the Earth itself.
Oh, it's just a plate.
No. Okay, so let's imagine 这个是地上是这个地上有一个 layer and layer and layer and layer and layer and layer. Alright. The top layer is known as a plate, the tectonic plates. Okay, the tectonic plates which are constantly moving. Okay. What? what about Turkey? What's happening in Turkey? Is there another earthquake in Turkey? Is it? What's happening in Turkey? Whatever. Anyways, because of convection current, the tectonic plates are constantly moving. We know for a fact that Earth's core is very hot, right? Right. And it means to say the particles that are closer here, once again, should be heated more, right? And when they're heated more, once again, they become less dense, right? And then what happens is the cooler part of the mantle will go down and then the whole thing will restart again, right? But of course, this is not as vigorous as what's happening in the Maggie pot lah. This one is very, very, very slow movement, but they are constant. Yes, they are very big and they are very heavy. So, but they are definitely moving. This explains why the tectonic plates are never in the same position every 1,000,000 years. In fact, if you go Google right now, last time they say lah, no, the Earth is not moving. The ground below Earth is moving. So last time they say, right, there was no different continents, you don't know, Africa, Europe, all these kind of things. So all of them was one big piece of land. But because the tectonic plates are constantly moving, they separated and eventually drifted around the Earth. Yes, now you know another power of physics and science. Right, so it's not just subjected to the water here. Actually, the mantle is moving. So okay. Copy everything. Okay, then the final thing that we're going to learn about today is basically radiation already. Now, whenever you see the word radiation, sorry, let me rephrase. Whenever you see the word black, white, or silver, straight away, I want you to think about radiation. Okay, for sure, they test your understanding on radiation area. If you see the word black, white, or silver in your exam, for sure. Of course, I've seen the papers 1,000 times. For sure, black, white, or silver. Just like if you see the word float or sing, they are testing your understanding of density. But if you see the word black, white, and silver, for sure they're testing your understanding of radiation already. Known fact, 100%. Trust me, I've done it 1,000 times. Okay, but anyways, in order to understand how black, white, and silver works, first and foremost, let's imagine today you and a friend, a dumb friend once again, goes to the beach. Today, if you go to the beach on a sunny day, what color will you wear?
White.
Good. Why will you wear white? Good. If you're a smart student, as illustrated here, right? Oh, forgot to wear the forest too. Yes. For sure. The science student. And then you have your idiot friend. Let's say your idiot friend is here. He wears black color t-shirt. We all kinds. Right. So if your friend is an idiot, right, and you guys both go to the beach for a hot sunny day, right, what happens is, right, black is actually the best absorber of heat. They absorb a lot of heat, and because they absorb a lot of heat, what happens is the heat will be emitted. It will be emitted back into the body. The heat will be emitted back into the body. Yeah, for sure. More or less, there's some contribution to it, right? And then for you, what happens is, right, white is actually the best reflector of heat. I mean to say, right, of course, it's not going to reflect everything. It may reflect some, but some heat will be still emitted inwards, very little amount of it. Okay, but most of it will be reflected. In other words, white is actually the best reflector of heat. White is actually the best reflector of heat. Is that why planes tend to be white in color? Yeah, it could be because planes are flying in very high altitudes. Oh, sorry. Of course, you won't wear the silverware, right? No, gray is gray, bro. Silver is silver. Silver is like, okay, in terms of silver, right? You know, like when your parents park their car under the sun for a very long time, usually they put the windscreen thing, right? Have you ever seen the big silver reflector thing? Why is it silver color? Why don't they make it black or white? Yeah, because silver is actually like a mirror.
Silver better.
Yeah, theoretically. Yes, theoretically, silver is actually the best reflector. Okay, like for example, mirrors and everything. Yeah, mirror is a silver. Mirror is a silver and reflects all the light. That's why you can see yourself. Because if you think about it, how does a mirror work? The mirror works by light going in and then it reflects back into you. Right, so silver is actually the best reflector of heat. Okay, but obviously you're not going to wear a silverware unless you go disco dancing, right? So white is the next best option already. Great. So from here, if you look at the statements, guys, radiation is a transfer of heat through light. When light is emitted, heat is present due to infrared. Guys, whenever you see this word, infrared is everything related to hotness. The reason why you put your hand under the sunlight, you feel hot, is because there's infrared beaming onto your hand. And a lot of people, they say that, oh, it's very bright today, so it's very hot. Usually, when it's very bright, it's because you have a lot of visible light going into your eye. But the reason why it's very hot is because there's a lot of infrared beaming down onto your hand. So that's why you feel hot. Okay, light and infrared is part of the electromagnetic spectrum. all electromagnetic waves do not require a medium. Do not require a medium means to say they are the only one which can travel through space. Okay, so radiation, all direction, and the only one that can travel through space. Okay. Okay, then this one here is basically this you must know, guys. They for sure test you on. They won't just simply test you on radiation. Usually they don't test you. If they test you on radiation, right, for sure they ask about black, white, and silver. 100%. You must know this. Okay, black is essentially the best emitter of heat because it absorbs most of the heat to emit it back into you, right? And white is essentially, silver is essentially the best reflector of heat. They are both extreme ends. So if it's best of one thing, it will be worst of the other thing. Best of one thing, worst of other thing, best of one thing, worst of other thing. Okay? A very simple experiment to describe how black, white, and silver emits heat differently is by having a metal cube that is painted for 3 different colors. Black surface, white surface, and also silver surface. Today, if I pour 100 degrees hot water into it, and I take a thermal gun to measure this, and also measure this, right? Which one do you think will be the hottest? The black will be the hottest one, right? Why? Because black is the best emitter of heat. It can emit a lot of heat upwards because it absorbs the most heat. So it can emit a lot of heat upwards. Okay, so this one is that. And the final thing here is basically thermal equilibrium, guys. Thermal equilibrium is the reason why when you hold your boyfriend's hand or girlfriend's hand, you feel hot or cold. Oh, because it is. Let's imagine today you're a single guy who's never held love before. Right. So let's imagine that, right? Let's say today you hold onto a metal rail. If you ever hold a metal rail before, you always feel that it's a bit cold, right? Why is it cold? It's because your hand, which is hot, is actually transferring more heat to the cold metal rail than the metal rail is transferring heat to you. So essentially, there is a net transference of heat energy to the metal rail. But if you hold onto the metal rail long enough, right, eventually, what happens is thermal equilibrium will take place where the amount of heat energy you provide will be the amount of heat energy you receive. Then you won't feel hot or cold anymore because this is what we call thermal equilibrium. Okay? So if you look at the statement here, an object is at constant temperature when the amount of energy it receives is the amount of energy transferred away. For example, this one thing, thermal equilibrium. Yes. So if like what Evan says here, right, if you ever go to the toilet where someone is already sitting on it, right, what happens is the heat energy is transferred from the ass to the seat. And then when they stand up, when you sit down, you still feel the heat being transferred to you. Right? Because eventually both objects that are in contact must reach thermal equilibrium. Okay, everybody? Humans have sweaty palms because our hand is too hot already. When our hand is too hot, it will secrete sweat to reduce the temperature. Right. Hey, but I tell you, some people, right, they have 24/7 sweaty palms, it's because their sweat pores are too enlarged already on their hand. So they constantly sweat. I had a friend who did the same thing also. And then I think there is a way to reduce the sweat pores on it. Or was there no way? Can't remember. Don't take my word for it. But yeah, I had a friend also who had the same thing. Her hands constantly sweaty. And if the doctor said it's because her sweat pores are too big. So we keep sweating. For sure, no bro. The sweat pores are like, it's like micrometers. 当然你可以看到叫喘动了，有没有？Yeah, I find that girls usually have sweaty palms more. Maybe it's because they are more warm-blooded. But wait a minute. according to my story just now. Right, so I don't know, but usually 女生很冷 is because it's that time of the month. It's because the hormones. Yeah, serious one. Yeah, when the hormones are imbalanced and everything. Oh, I think I read something online before that said if your hands are always very cold all the time, it's because there's not enough blood circulation. So what happens is like, no, it's not menopause, bro. Menopause is a totally different thing. Menopause is like when you cannot produce ovum anymore. I shut up, like you don't even learn biology, you don't know anything, like. But anyways, oh shit, what was I saying? Oh yeah, I read online before because I also like that. When I'm young, right? Not even until now, my hands, right, they will get cold very fast, especially in a relatively not even cold room, a relatively cold room. My hands and my feet get very cold. They say, right, it's because there's not enough blood circulation, so your body prioritizes heating up your body only, and then all the blood flow. But then again, once again, I'm not exactly sure because I'm not an expert. Don't take my word for it. But as I can recall in my memory, I remember that it's because there's not enough blood circulation, so the body prioritizes the organs, right? So they'll just like not pump so much blood to your hands and feet anymore. That's why they are always the first to go cold. But you can go have a look at Google. I just search out why are my hands always cold? What's the reason? They will give you a lot of answers. I searched it before because I was very curious. And then they said that it's because, if I can remember correctly, there's not enough blood circulation. So the body is very smart. They'll prioritize your body organs and yeah. So of course, like if your here is cold, then you're about to die, right? So they always prioritize here. Okay. Yes, everyone. Yeah, you can start attempting the first question. I think I'm not going to discuss it now. You can attempt as much question as you can. Next week, we're going to go through everything here. Once we're done with this, we'll take one more week to revise all the thermal physics. Then we're going to go for a test already. Okay. So Chloe, if you're watching this during recording, please make sure you read everything. Yeah, we're going to go for test already. Okay, yeah. Guys, start attempting the question now. We'll discuss the answers next week for this one. By the way, I want to highlight this question here. I want to highlight this question here, guys. This one here, the students always get this mistaken, which is the same question for the next one as well. Describe how you would use the apparatus to compare the abilities of two surfaces to absorb infrared radiation. You're basically going to write a small little step-by-step guide on how you're going to use the apparatus to conduct this experiment. You can write it in point form. They don't discriminate, right? But yeah, just make sure you write the step-by-step. So if you look at the mark scheme here also, it's someone like that. Someone like that. Usually the students will get this wrong. So it's best if I just tell them straight up now. The next question will be a similar question. You'll need to attempt it. Okay, guys, please attempt this question right now. We'll discuss this answer, then we'll call it a day already. Okay, bye-bye.
I'll take a break. How do I say it? Supposed to green flag.
Let's go through this last question and call it a day already, guys. If you look here, they ask you to describe how you would use the apparatus to compare the abilities of two surfaces to absorb infrared light. You know for a fact that the dull black one, like I said, you see the word dull black and shiny white, for sure the testing and understanding of radiation already. So you're supposed to describe how you're going to use the apparatus. So if I were to say something, I'll say something like, place the Bunsen burner equal distance between the two surfaces and heat them up at the same time. After a period of time, measure both temperature changes. Temperature changes.
What is
This thing. Oh, this thing here is the thermometer rest. You know, like if you measure the temperature of the liquid, you cannot have the thermometer touching the surface, right? I mean, look more professional lah. They obviously didn't want to draw the hand there, right? So, oh shit. So what happens is you put a what's it called, a rester here, so that the thermometer can rest on top here, and then it can measure the temperature change. And then obviously state the results you would expect. What results do you expect here?
Yeah.
Portion. Dull black. Higher. Portion. Okay. Final reminder, Evan, next week don't come to the center. It's going to be online class. If you come to the center, then it's good luck, have fun, and enjoy already next week. What the? Nice.
Yeah,
Let him come to the center then. Hey, how come today is the same thing again? Okay, anyways, this is where we're gonna end today, guys. We'll stop here.